for the kind introduction. And thank you very much for giving me the opportunity to present today. So as you already said, my name is Michael Chabanov, and I'm from the Goethe University in Frankfurt. And today I will talk, or the title of my talk will be General-relativistic hydrodynamics of non-perfect fluids, 3+1 formulations, and viscous black hole accretions. And this is essentially the work, what I'm working on with Luciano Rizzella and Dirk Rischke here in Frankfurt. So to give you a quick overview, sorry. Okay, now it's working. To give you a quick overview of the talk, so the essential idea of the talk is to explore how non-perfect fluid effects can be incorporated into simulations of astrophysical sites where also general relativity plays a role. And at the beginning of my talk, I will try to motivate this idea and state why non-perfect fluid effects might be interesting in binary neutron star mergers, for example, and yes, motivate the whole idea from a physical point of view of why this might be important. Furthermore, I will then move on to to actually some technical details about how the equations have to be formulated in order to be solvable with the codes that we use already, and in how to do this in the best way. Furthermore, I will present a numerical example of bulk viscosity that I've implemented in such a code, and present to you a few test cases in order to verify the implementation. And finally, I will present to you a test in general relativity, namely a black hole which is accreting a bulk viscous fluid, and show you how this can be used as a test case for the bulk viscous equation in a numerical implementation. So let's start with the motivation. I thought I will start by making a few remarks on neutron stars in general. So neutron stars are very, very dense objects which are created in supernova explosions. When very massive stars having masses of around 10 to 25 solar masses burn their nuclear fuel in their core, and essentially an iron core is building up. This can be done up to a threshold where the mass of the iron core is too heavy to be supported on its own, and it starts collapsing. This is called a core collapse supernova, and essentially in such a process, neutron stars are born. What is left behind after the supernova is essentially this the remnant of this dense iron core, which is a neutron star. Radii for a typical mass for such a neutron star is, for example, 1.4 solar masses, and the typical radius ranges from 10.5 to 13.5 kilometers. So you really have a lot of mass compacted into a very small amount of space. An currently open question in the field is the maximum mass of such an object. So if you have a non-rotating neutron star, how heavy can it get? And the current estimates range from around 2 solar masses to 2.3 solar masses, and this is also called the so-called MTOV, where TOV stands for Tolman, Oppenheimer, and Volkoff. Neutron stars are usually observed as pulsars, which are rotating neutron stars and which emit electromagnetic radiation along their magnetic field axis. And in those specific configurations, the magnetic field axis is misaligned with the rotational axis, such that whenever the axis sweeps the line of sight of the Earth, we get pulses, and very regular pulses. And actually, this is how the first neutron star was also observed. As I said, an ongoing question is the MTOV mass of the neutron star, which is directly related to the equation of state of dense QCD matter. And in this scheme, for example, or in this picture that I'm showing you here from Friedrich Weber, you see a schematic composition of the different layers of a neutron star. in general, a neutron star can be divided up into two broad regions. You have the crust and the core, and while in the crust nuclei are present, they start slowly they start getting heavier and heavier the further you go into the crust, and finally, when you start reaching the core, you can reach up densities up to the nuclear saturation density and above, and those heavy nuclei start to dissolve, such that you start getting dense nuclear matter. The traditional model for the core of the neutron star, for example, which you can see at around 1 o'clock in the model, is composed of neutrons, protons, and electrons and muons, and what is called traditional nuclear matter, traditional neutron star matter. So those are neutron stars, and neutron stars also, a lot of neutron stars have been observed in binary systems, and those binary systems eventually lead to a merger due to the emittance of gravitational waves, which reduces the angular momentum of the system. And as soon as and when those neutron stars start to merge, we get observables from a wide range of different physical processes, which make neutron star mergers a very rich laboratory for all kinds of fundamental physics. As already said, gravitational waves can be measured from binary neutron star mergers, and in fact, the first binary neutron star gravitational wave event was measured in August 2017, namely GW 170817. But other than that, also binary neutron star mergers are known as the astrophysical production sites of heavy elements, where the mass ejector of binary neutron stars is very neutron rich, and when flowing out undergoes radioactive decay that can power the so-called kilonova. And as already said, neutron stars are very dense objects and essentially probe the QCD phase diagram at or cold neutron stars or single neutron stars probe the QCD phase diagram at 0 temperature and baryonic densities above the nuclear saturation density. But during neutron star mergers, also very high temperatures can be reached, for example, a few tens of MeVs. So binary neutron star mergers even probe the QCD the dense and hot QCD phase diagram, QCS. As an example of such an binary neutron star merger evolution, I wanted to quickly show you here the evolution of a binary neutron star, where the total mass of this binary lies below 1.2 mTOV, where mTOV is the maximum mass a non-rotating neutron star can have. So after the merger, the remnant object is highly differentially rotating and called the so-called supramassive neutron star. The supramassive, in this case, supramassive neutron star means that the total mass of the object is low enough that such a neutron star can be supported through uniform rotation only. If the mass, for example, the total mass exceeds this limit of 1.2 mTOV, you get a hypermassive neutron star, which has to be differentially rotating in order to be stable. Otherwise it collapses to a black hole. So we have this object we have this remnant object after the binary neutron star merger, which is differentially rotating, and slowly, due to magnetoturbulent angular momentum transport, the differential rotation of this remnant object is transformed into uniform rotation on time scales of 1 millisecond up to 1 second. And what is left in the end is a uniformly rotating supermassive neutron star, which again is stable because its mass is not exceeding this 1.2 solar mass, 1.2 mTOV line. But during that whole merging process, we are now in the third stage of this diagram. Due to dynamic interactions in the violent phase of the merger, matter was ejected, and a lot of matter was ejected, and not all of that matter was able to escape, and some of it remained bound in a donut-shaped form around the remnant neutron star, which is called the torus. So, and this torus is slowly but surely accreting on the remnant neutron star, and can eventually and can maybe exceed this limit of gravitational collapse that we have here. So depending on the mass that is accreted from the torus, you can either collapse to a black hole, or you can form a stable, uniformly rotating neutron star. And having described that process, I'm going back to the actual topic of my talk. So we want to explore the effects of non-perfect fluids in the merger process of binary neutron stars. So the first question we want to ask is: are dissipative processes present at all in some stage of the evolution of a binary neutron star merger, and do they play an important role? So the answer to that question is yes. There are possibilities to include effects of non-perfect fluids in binary neutron star mergers, and one of those possibilities, or one of those dissipative effects that plays a role, is effective shear viscosity. So in the early stages of the binary neutron star merger, the magnetic field of the merger gets amplified very strongly, and also turbulence is injected into the flow. Due to that combination of turbulence and high magnetic fields, the turbulent state can essentially be sustained, which leads to an effective shear viscosity, which is present in the outer layers of the binary neutron star merger remnant. And this means that in order to qualitatively and quantitatively capture the most important effects in the post-merger evolution of remnant neutron stars, one has to be able to model those effects. But the problem is that MHD turbulence is occurring on very small scales, indeed such small scales that we are prohibited by resolution in order to resolve those. So we have to take a different approach in order to tackle that problem. And one of the approach that is described here is the approach of effective shear viscosity. So we can, instead of resolving magnetohydrodynamic turbulence, which is present in the post-merger remnant, we say that the global effect of this turbulence on the evolution of the merger remnant is acts in the form as a shear viscosity, and because of that, we go to non-perfect fluid dynamics and evolve the remnant neutron star with shear viscosity. For example, what I'm showing you here in those plots is some results of the paper of Fujibayashi et al., who incorporated an effective shear viscosity in their long-term evolution of neutron star merger remnants. Here they chose an approximately 3 solar mass remnant with a torus of 0.2 solar masses. And if you focus on the plot on the bottom left, this shows the angular velocity as a function of radius here. And you can see that at 0 milliseconds, which is the time when the violent neutron star merger phase has ended, and also the gravitational field set it to an approximately stationary state, you can you start that evolution at this point. And as you can see, shear viscosity is removing this differentially rotating profile where the core is slowly rotating in comparison to the to a more or less outer layer at around 10 kilometers. This differential profile at 0 milliseconds is completely removed on the order of 10 milliseconds, and you get a beautifully uniformly rotating profile in the center of the remnant neutron star. And an effect that can be observed due to this very rapid profile transition in the rotation in the angular velocity is the generation of a shock wave. And if we now look at the top plot on the right, you see an XZ slice of the domain at 20 milliseconds, and you see that around approximately 800 kilometers away from the remnant, you see that you see this density wave or that shock wave traveling outwards. And if you evolve further in time, which is shown in the plot below, you see that this density wave at 50 milliseconds is sweeping a lot of matter outward. And the ultimate goal of such studies is the long-term evolution of binary neutron star merger remnants and the accompanying long-term mass ejection process. Another very interesting inclusion of dissipative effects that could be done in binary neutron star mergers is the question whether bulk viscosity is active or any dissipative process related to actual microphysics is acting in a binary neutron star merger. And in that paper of Arford and al. In 2017, it was shown that harmonic density oscillations in the neutron star actually can lead to can generate a bulk viscosity which is coming from beta processes being off equilibrium. And always when those beta processes try to re-equilibrate, they lag behind those density oscillations. And in this whole process of harmonic density oscillations, entropy is generated in the form of bulk viscosity. And the question is whether the bulk viscosity is large enough, and whether the timescales on which this bulk viscosity is acting actually are low enough in order to have a measurable difference or a qualitative difference on the evolution of the binary neutron star merger remnant. And what was shown, and there are a few conditions in order for this to be true. So first of all, the timescale of those density oscillations has to be comparable to the dynamical timescale of the whole evolution of the remnant. And the dynamical timescale is of order of 10 milliseconds of approximately, and this is the time where most of the energy is emitted in gravitational waves. Also, a necessary condition for this re-equilibration process to have the right re-equilibration time is that neutrinos have to be free, and that the temperature has to fall into the specific zone between 4 and 7 MeV. If you now focus on the plot to the right, this is a plot this is a logarithmic plot of the quantity T flow, which can be taken as synonymously for the timescale of density oscillations. And you can see that in the middle region of the plot, in those two separate regions, essentially the timescale is of the right order of a few milliseconds. What is shown, the green contour line shows you where the rest mass density exceeds the value of nuclear saturation density, which is also necessary for the density oscillations to carry enough energy. And finally, what you can see, the gray and the red contours are showing temperature contours, where the red contour is showing the 4 MeV contour, and the gray contour is showing the place where the temperature exceeds 7 MeV. And you can see that perfectly in this region where also the timescale of density oscillation peaks, also the right temperature is reached, and the nuclear and the rest mass and the density is also in the right region. So this essentially hints that the timescale of those that the timescale of bulk viscous dissipation in binary neutron star mergers might be really on the order of the dynamical timescale.
Sorry, Mikhail, there is a question, I think.
Yes.
Please go on.
Yes, I wanted to know if there is a known reason why these specific temperature region has to be given.
Yes, the reason for that is that above that temperature, so if you are, I think, if I understood it correctly, below that temperature, the bulk viscosity itself won't peak. So you want the bulk viscosity to have a maximum value, which can't be reached below that temperature. And if you go higher in temperature, neutrinos can be trapped, which will lead to very fast re-equilibration rates. And this again will shift the peak where the bulk viscosity coefficient is peaking to lower temperatures. So essentially, these conditions are identified by seeing where the bulk viscosity has a maximum, and the relaxation and the re-equilibration time of those beta processes is in the right window on the dynamical time scale in order to maximize the bulk viscous, the dissipation through bulk viscosity.
Okay, thank you.
I hope that helped you. Okay, so let me move on. So yes, so this was on the motivation why dissipative effects might be important. To summarize, you have either the inclusion of shear viscosity to model in order to model magnetoturbulence, or you also can have a bulk viscosity originating really from beta processes being of equilibrium in density oscillations of binary neutron star merger remnants. And now let's talk about how which formalism there is to include those dissipative effects and how this could be done in general-relativistic simulations. So I'm starting here very slowly by talking about the basic building blocks of relativistic hydrodynamics. So those are essentially, if you look at the two equations, on the two equations relatively in the center of the slide, you see those are the rest mass density current and the energy momentum tensor. And of course, the evolution equations are obtained by the divergence laws of both of those quantities. And now what we want to do is to extend the ideal definition of those quantities by dissipative effects. So essentially what we do is because of that, we include those so-called dissipative fluxes in the form of a bulk viscous pressure, which is denoted by the capital pi. We also add an heat flux by Q mu and a shear viscous tensor, which is added to the energy momentum tensor by pi mu nu. We are working here also in the Eckert frame, and because of that, there is a heat flux and the rest mass density current stays unchanged. But because we have extended the space of variables in our system, of course, we need suitable closing relations in order to be able to solve the system. And a simple idea which essentially is the same as going from ideal non-relativistic hydrodynamics to the Navier-Stokes equations, is to define those dissipative currents as the same relativistic analogs that are also that can be found in the Navier-Stokes equation. I think there's another question. Sorry, is there another question?
No, it's not a question. I was telling if you can use your mouse
Right.
For better clarification. Yeah, thanks.
Okay. Yes, that's a good idea. So essentially, we can define those. For example, when talking only about bulk viscous pressure, we can define this quantity as the relativistic analog of the bulk viscous pressure in the Navier-Stokes equations, which is just an minus the bulk viscosity coefficient itself times the fluid expansion. And this can be analogously done for the heat flux and the shear viscosity. And we refer that to a first order theory because this is the definitions of the dissipative fluxes is of first order in gradients of the fluid variables. The problem with that is, though, that this theory is uncausal and unstable, which can be already seen here, because you have instantaneous changes of the dissipative fluxes coming with the changes in the gradients of the fluid. So the system of equations is parabolic and therefore has infinite propagation speeds. In order to solve that problem, one can go to a second order theory, where the main difference now is that the dissipative fluxes, for example pi, are treated as full-fledged evolution variables and are evolved together with the other quantities. So, for example, here this is a simple relaxation type equation for the bulk viscous pressure, where we have to introduce a time scale, namely the relaxation time tau pi, on which the bulk viscous pressure is converging towards its Navier-Stokes value, which is the same as in the first order theory. So this theory was shown to have no generic instabilities, and this also implies the causality of the system for a suitable choice of transport coefficients. So this is actually what we want. Sorry, okay. So this was a very heuristic motivation of how one could include, or how one could extend the equations of how one could use second order theory. But there's also a more formal way to do that, and this is based on the entropy, on the extension of the entropy current. So here, for example, you see the definition of the entropy current for the ideal fluid case, and we now try to extend it by this R mu. Being still first order in dissipative fluxes, this R mu is restricted to be Q mu. And if we now apply the second law of thermodynamics, namely that entropy has to be, the entropy generation has always to be positive, we arrive again at the Navier-Stokes equations, or the first order theory that we had before. So we see that the first order extension here again is not enough, and we start adding new contributions to the entropy current, namely all contributions which are of second order now in dissipative fluxes. And if we do that, we and follow the same procedure as before, we arrive at causal dissipative relativistic hydrodynamics equations, which in their core have this relaxation type form that I've shown you on the previous slide. Also, I want to make
sorry, I interrupt you. Could you please, because you know that in the heavy ion communities, this is written as SU mu, but here you got S and rho. I think it's good to explain this.
Okay, yeah, I'm sorry. In astrophysics, we are usually evolving the rest mass density, which is denoted by rho here. And so this whole quantity is the entropy density of the fluid, and this makes this little s the specific entropy of the fluid.
Thank you.
Okay. So there are also more sophisticated approaches to deriving those equations, while the general form of the equations actually will remain the same. And I want to just briefly mention two of them. One was firstly given by Bayer et al. In 2008, which is known as the BRSSS. And this R I will explain in a second. So in this approach, the energy momentum tensor of the fluid is extended systematically with terms being of second order in gradients of fluid variables. So what you really do is you add terms to an energy momentum tensor which are second, which have at least, which have two or less gradients of fluid variables, for example, the fluid. And you do this in a simple way, just you can think through that the theory was, again, as the Navier-Stokes equations, uncausal and unstable, and that's why a so-called resummation was introduced. And this is this small r here, which led to a causal and stable, which led to causal and approach to the problem is
Sorry, I have some problems in hearing your voice. I don't know if this is my
yes.
problem or everybody's problem.
Of discontinuous states, or so-called shocks, converge to the weak solution if convergent at all, if and only if a conservative scheme is adopted. And this means if in your numerical solution discontinuities or shocks are present, your numerical solution will converge to the right solution only if your equations are written in such a form, which is called a conservative form. You see, you have where U is the so-called state vector, the Fi's are the flux vectors, and S is the source vector. So this is already a desirable formulation, because we know that hydrodynamics naturally develops shocks, and we want to be able to accurately model those shocks on the computer. Furthermore, some numerical, a large amount of numerical codes is employing the so-called 3+1 splitting of Einstein's equations, where those equations are where you essentially decompose space and time. To briefly explain to you how this is working, you decompose your. If you look at the picture in the slide, you see that space-time is sliced into different hypersurfaces of constant time. This is, for example, denoted by sigma t and sigma t plus dt. And by doing the slicing, you can introduce a so-called normal vector or an Eulerian observer, which sends normal to each, which is normal to the hypersurface, which is normal to the hypersurface on each point of the domain. By this way, you can also define a purely spatial metric, which only describes one hypersurface, and this is denoted by gamma mu nu, and this normal vector is denoted by n mu. So, having introduced those quantities, you can now decompose your coordinate observer vector, which is given by t, in terms of your normal vector. So you simply split your coordinate observer into a part parallel to the normal observer, and accordingly a part which is purely spatial. This purely spatial part is called the so-called shift vector, and the projection of t onto n is the so-called lapse function, which essentially measures the passage of time between two adjacent hypersurfaces. Since many numerical relativity codes employ this formulation to solve the equations, we also want to use this formulation in order to solve our equations numerically. Especially what we want to do is decompose our non-perfect hydrodynamic equations into components parallel to n or parallel to the Eulerian observer, and on two projections which are purely spatial. And this is essentially what we have done. Yes, on this slide you see the final result. But let's start looking at the green box on the top right corner. Here you see how the spatial metric gamma is used to project the heat flux and the viscous shear tensor onto spatial hypersurfaces. And this is at the core of the 3+1 formulation. And what we want to do now, we want to have evolution equations for those quantities here, q perp and pi perp, which are written in a conservative form, given in this blue box above here. So this is our final goal. And the result you can see in this depiction, in this form of the state vector. Essentially what you see furthermore on the slide are definitions of the state, flux and source vector, which can be directly plugged into this conservative equation in the blue box above here. And there are two things that I want to remark, and those are Sj is the projection of the energy momentum tensor onto spatial hypersurfaces. Is essentially the same what we also do with the dissipative fluxes, and you see that its definition is changing due to the incorporation of dissipative effects. Especially, you see that this Sj, which is also present in the ideal case, gets contributions from for example q perp, which is the quantity here in the green box. And another difference, of course, is the extension of the whole system of equations by the new constitutive relations that we have for our dissipative fluxes. Yeah, so those are in principle all the changes one has to make to a conservative formulation or conservative 3+1 formulation of ideal hydrodynamics in order to go from ideal to non-perfect. And all differences and non-perfect effects can be usually accounted in the source terms, where you, for example, see, if you look at my cursor in this delta function here, for example, a variety of different terms can be included into model different contribution or different orders of second order of hydrodynamics. So this was from the analytical side, what has to be done in order to incorporate dissipative or non-perfect fluid effects into codes, which also solve Einstein's equations simultaneously. And now we want to perform a numerical experiment where we actually test our formulation. The code that we are using for that is the so-called black hole accretion code, which was developed by Oliver Port in our group. And this is a multidimensional Fortran code, which solves the equations of general-relativistic magnetohydrodynamics with a fixed space-time background. So even though this code fulfills all requirements to be coupled to an Einstein to a solver which solves the Einstein equations, here the space-time is not evolved, and it's taken to be stationary. Furthermore, this is a finite volume code, which simply means that you evolve cell averages rather than cell centers in the code, and high-resolution shock capturing methods are employed here. Also, a quite neat thing about that code is that that adaptive mesh refinement is implemented, which simply means that you can control in regions that you can control you can concentrate resolution there where you need it the most. So, for example, you expect a fluid variable change very sharply in a certain region. You can locally refine it with adaptive mesh refinement. What you also see in the slides are the definitions for the state, flux, and source vector. The ones, now in comparison with the ones I've showed you before, the dissipative contributions are missing, and you have an additional evolution equation, but which stems from the evolution of the magnetic field in the approximation of infinite conductivity. Yeah, so essentially, now we want to modify the system in order to include bulk viscosity. And this is done essentially in 2 steps. So the first step again is to add an evolution equation for bulk viscosity to the system. And here you can see in the last entry of the state vector that we include, or in the last entries of essentially all those vectors, that we include the evolution of the bulk viscosity in the proper form. But also we have to couple this bulk viscosity into the fluid. And as you can see, and as I mentioned before, the definition of those state variables change by including this bulk viscous pressure. But if you want to change the definition of those evolved quantities in the code, this is a quite deep change in the code. So there's actually a simpler method to do that without rewriting the definitions of those code, without making such deep changes. And and this can be done simply by observing that the bulk viscous pressure is always occurring next to the normal pressure, and is never having a separate contribution. So we can actually say that instead of modifying the definition of those quantities here, of, for example, the projection of the energy momentum tensor on the spatial hypersurface, we can modify simply the equation of state of the fluid, which is giving you the pressure, which is providing you the pressure. So now we simply evolve the same system of equations simply with a different pressure definition, which you can see, for example, here. We have an effective pressure denoted by P star, which is just P plus pi. And by doing that, we can the main infrastructure of the code can be left as it is, and we can include dissipative bulk viscosity into our code.
Sorry, if you got the shear viscosity, this is somehow I can imagine that it's going to be harder, yeah?
That's correct. Yes, if you want to include shear viscosity, this simple trick is not possible anymore, and you actually have to change the definition of the evolved variables, which which also means that you have to a main feature of those relativistic codes is that the evolved quantities are not those that you actually plot or that you actually look in the end for. For example, you have to go from Sj, which is evolved, to your fluid for velocity, which you want in the end to analyze, and this requires a so-called contour prim, because also you need those quantities in order to calculate those fluxes here. And essentially, this procedure has to be altered if you want to include shear viscosity.
Thanks.
Okay. And the final thing that one has to take care of when including bulk viscosity is the implementation of gradients in the source terms. So in the upper blue box, you see the 3+1 decomposition of the fluid expansion, which is present in the source terms of the bulk viscous equation. And you see that those the 3+1 decomposition leads to, for example, this divergence of the this spatial divergence here, but also a time derivative is present in this lambda term here, and you have to properly take care of that. So for the time derivative, we use as you can see in the red box, we use a simple second-order central differencing scheme for the time derivative. But for the spatial gradients, we have to take care of the fact that we have a finite volume code and cell averages are evolved, which means that we average this fluid divergence, the spatial fluid divergence here. We average it over the cell volume, which means we integrate over a cell, and by doing that, we can transform the volume integral through Gauss' law into a surface integral, and simply calculate this divergence by calculating the fluxes at the cell surfaces. Yeah, this was just some few quick remarks on the discretization procedure. I don't want to go further into detail here, but if there are any questions, of course, just feel free to ask, or we can talk after the presentation about that. So let's move on to testing. And here I'm showing you the parameterization I'm employing for the tests. And as usually done, I'm parameterizing the bulk viscosity in terms of the entropy density, which is denoted by S here. As I see now, this might be a little bit confusing since this is not the same S as Masoud, you asked about earlier in the slides. And the relaxation time is can be simply calculated from the mean free time between collisions of the fluid. And the fluid is an ultra-relativistic ideal gas of gluons. So essentially what I want to show, I want to show you the test case of a shock tube here, where you have a temperature discontinuity and a continuous velocity, and you see which shock structure will emerge. So first of all, I want to show you the low viscosity case, and here the entropy over the bulk viscosity over entropy density ratio is about ranges from 0.02, and we also take the value of 0.01. And as you and to the left, I'm plotting the evolution. I'm plotting the final result at 3.2 Fermi over C. And as you can, yes, and what's also the blue line shows the initial data. The solid lines show the evolution that we obtain with Buck, and the dashed lines, which can be hardly seen in this plot, are a comparison to the so-called relativistic lattice Boltzmann method, where we got the data from a paper from Chabanov et al. In 2020. And this data is serving as a comparison of our model to see if the implementation is correct. And as you can see already, the qualitative shock structure or the wave pattern is preserved. We see this beautiful rarefaction wave to the left and the shock front to the right. And but if we zoom in, we start seeing differences between the relativistic lattice Boltzmann method and our Buck implementation, which can be seen in the middle plot. Even though the differences are very, very small, as you can see, and they're just present in the thickness of the shock layer but of course for higher viscosities the differences are getting larger. But other than that, the agreement is very, very good. Also, as you can see in the right plot, a plot of the viscous pressure over the normal pressure, and you see that this pressure is highly generated at the shock front, while the viscous pressure has a negative sign in the rarefaction wave, in the rarefaction fan, because the fluid is expanding in that region. And now let's move on to high viscosities, which shows a slight difference to the case we had before. You see that the wave pattern in the left plot, you see essentially that the wave pattern is more smeared out in this case, as you would expect for higher viscosities, but and the qualitative agreement seems to be very good in this case too. But again, if you zoom in onto the shock region, you actually see some differences which were not present before. If you look now into the middle plot and you focus onto the red curves, which show the model for the high viscosity case, you see that such a double shock structure is emerging, and this double shock structure in the Buck solution essentially is related to the fact that the dissipation at the beginning of the initial state is that high that it smooths out the gradient too quickly and makes the former discontinuity survive for a longer time. Essentially, this means that the pressure and the velocity, for example, in the regions of the discontinuity at the beginning of the simulation is relatively constant, and this makes the discontinuity propagate further in time. The core of that problem is actually related to the moment expansion of the theory that we are using, and it's related to the amount of characteristics that you have in the system. By extending our ideal fluid description with bulk viscosity, we introduce or modify the characteristics which are present in the systems. For low viscosities, those additional characteristics, which are also additional waves, have a very low amplitude and essentially don't modify largely the whole wave pattern. But as viscosity gets greater, those additional waves start to gain in importance and can eventually change the wave pattern that is emerging in such a shock tube problem. This is essentially the same. This is also happening here at the foot of the shock wave, where you see that in comparison to the relativistic lattice-Boltzmann code, which is able to resolve this foot of the shock, we have a discontinuity in the beginning here. Also, what is important to mention is that due to the fact that we have a very simple relaxation time equation for bulk viscosity, the heat generated at the shock front is underestimated, as you can see here. The black dashed line shows the corresponding case for the relativistic lattice-Boltzmann method, and you see the underestimation quite clearly. As another test case, we performed the we calculated the so-called Bjerken flow in Bjerken coordinates, which is the boost invariant expansion in our case, of a one-dimensional fluid having an ultra-relativistic equation of state. And the good thing about that is also that in semi-analytic solution is available, which is denoted in the green box here. And moving on to the plot, you see here the bulk viscous pressure as a function of the Bjerken proper time tau. And the solid lines denote the analytic solution, while the dots show the solution that we obtained with Buck. And the dashed lines show the Navier-Stokes model, shows the Navier-Stokes value as also as a function of tau. And you can see that the dots lie pretty well on the solid line, and we are able with Buck to reproduce the semi-analytic solution quite well. So far we have only performed special relativistic test cases, and we have actually seen quite good agreement up to viscosity over entropy density ratios of about, let's say, 0.15, where this double shock structure started to appear. But for low enough viscosities, our code was able to reproduce the test cases quite well. But since those are all test cases in special relativity, we now want to move further on to a general relativistic test case, namely viscous black hole accretion. And I want to make a quick introduction onto that by showing you the ideal accretion problem. So this problem is essentially defined as a fluid which is accreted spherically symmetrically by a Schwarzschild black hole, and the whole process is stationary. Also, in polytropic equation of state is usually used. By having all of those restrictions, one can derive two conserved quantities which are present in the system, namely the mass accretion rate and the so-called Bernoulli constant, where omega is simply the time component of the covariant fluid flow velocity, and this is related to the gravitational potential of the Schwarzschild black hole. We can also derive a system of ordinary or this ordinary differential equation if we consider all of those restrictions. And what is interesting here is that a so-called critical point is appearing in the flow. This critical point should be distinguished from the critical point one usually has in phase diagrams, which is related to phase transitions. This critical point is just denotes you that the denominator of this ordinary differential equation is going to 0, and you essentially have a singularity in the problem. But yes, due to the fact that this singularity has to be removable, you have to impose a regularity condition at your critical radius, such that you get additional two conditions at your at the critical radius where the enumerator and the denominator have to be 0 at the same time. Having those two conserved quantities and those regularity conditions, one doesn't actually have to solve the ordinary differential equation, but rather the solution can be obtained by solving a system of algebraic equations. An example solution is shown here in this plot, for example, where you see the fluid velocity. The fluid is accelerating towards the black hole, but when the gravitational time dilation is so large, the fluid, as observed by an external observer here, again starts looks like it is decelerating towards the fluid and eventually reaches a velocity of 0 at the horizon. And now we want to move on to the viscous equations of motion, and we do that by first noticing that since we have viscosity in the problem, entropy is not conserved anymore. And because of that, we have to use an ideal gas equation of state, and we simultaneously also have to solve the hydrodynamic equation for energy, which was not necessary previously. Also, of course, we have to include the relaxation type equation for bulk viscosity here. Yes, but what's interesting is that the number of conserved variables stays the same. Simply the definition of the Bernoulli constant has to be changed, and we define the viscous Bernoulli constant in this form, which in the limit of 0 bulk viscous pressure is the ideal Bernoulli constant. Since we have additional equations now in this problem, we are not able to solve the system by a simple system of algebraic equations, and that's why we have to solve the full system of ordinary differential equations. What is interesting though is that the structure of the ordinary differential equation seems to remain the same. We have the denominator at least is the same, but we have a different speed of sound now, namely the viscous speed of sound, which is modified by the inclusion of viscous terms. So now the critical point is occurring at the place where the fluid velocity is equaling the viscous speed of sound. So a few words on the parameterization that we are employing. So we are using the parameters for an ionized non-relativistic gas of protons in equilibrium with radiation, and this parameterization could be naturally encountered, for example, in the era of recombination and shortly before recombination in the early universe. And the nice thing about that is that in the system, bulk viscosity naturally arises from adiabatic compression. And this can be understood because we have a mixture of a relativistic and a non-relativistic fluid. So if the whole mixture gets adiabatically compressed in the same way, due to their different prescriptions, the amount of temperature change in both fluids will be different. And afterwards, an temperature equilibration will be acting, which in turn will produce entropy in form of bulk viscosity. And yes, this entropy this bulk viscosity coefficient is given here in this red box. And for the relaxation time, we don't use the parameterization for a mean free path, but rather we use a parameterization which is to the third power in the radius. And I will later explain why we use that parameterization. Of course, during the whole evolution, we want the modified speed of sound to be less than 1 in order to be in a causal domain. Also, we will consider 5 different models. The most important about those models is that we have a reference model with a reference bulk viscosity and a reference relaxation time. And going from there, we will lower and higher the bulk viscosity while keeping the relaxation time fixed. And we will also lower and higher the relaxation time by keeping the bulk viscosity fixed. And in this way, we can see the different effects that those 2 transport coefficients have in this problem. So let me say a few quick words on how we solve the system. What we need, due to the fact that we have a critical point in the problem, we are not able to numerically integrate over this point. So what we want to do is start our integration at this critical point. And fortunately, due to the if we specify the critical radius and also the 2 conserved quantities, namely the Bernoulli constant and the mass accretion rate, we are able to formulate again an algebraic system of equations, which will lead us the state variables at the critical radius. And so we already have the states. We could also start integrating now, but still the first step in the integration will be prone to large numerical errors because we have to evaluate the derivatives essentially at the critical radius where small numerical errors are amplified largely. And because of that, we also want to have exact values for the derivatives at the critical radius. And in order to obtain them, we linearize the system and solve the corresponding eigenvalue problem, where the derivatives are obtained through the eigenvectors of the linear ODE at the critical radius. So to summarize, we have exact values for the states at the critical radius and also for the derivatives at the critical radius. And we can perform the first step of numerical integration to the right and to the left by simply using those derivatives. And all further integration steps are performed by using a standard implicit numerical integrator, in this case, a singly diagonally implicit Runge-Kutta method of order 4. So here, let's talk about the results that we obtained. And in the left plot, you see the relative difference in temperature compared to the ideal case as a logarithmic plot. So this is essentially tells you if if our viscous model or if our viscous models are hotter or colder than the ideal model. And as you can see, for large parts of the domain, the temperature actually is pretty close to the ideal model. While it's interesting, while the largest deviation is occurring close to the event horizon and can be up to 10 or 20% larger than the ideal value. Other than that, the difference is quite negligible. Yes. Furthermore, you also see the numerical error in the lower plot, and for that I want to say that the plots that you show here are obtained with bug. So what we have done before on the slide, we have solved the viscous accretion problem with an ordinary differential equation solver, and now we want to use this. Now we want to use this solution in order to test our bulk viscosity implementation in bug. So we use that solution, plug it into bug, and let bug evolve the solution. And if everything is correct and we did everything right, the solution should stay stationary and not deviate from the input solution too much. And this numerical relative error is shown in the lower plot on the left of the left plot. And you see that the maximum relative error in temperature is of 4%, and which shows, and the stationary state is also maintained, which shows you that our code is able to maintain the solution to a quite good precision. You can also, on the right plot, it's also interesting that I'm showing you the modified speed of sound, or the viscous speed of sound, which is sharply increasing towards the event horizon. And actually, we chose our models in such a way that the uncausal limit, which means viscous, this viscous speed of sound larger than 1, is reached somewhere around close to the event horizon, but below the event horizon, such that it's not falling into the domain of simulation. And here I want to show you the viscous pressure, the results for the viscous pressure. And let's focus first on the left plot, where you can see the logarithm to the basis of 10 of the bulk viscous pressure divided by rho h. But also you can see, and this is denoted in solid lines for all the different models. And the dashed lines denote the Navier-Stokes value divided by rho h for the model's reference, for the high viscosity model and for the low viscosity model. And let's focus first on large radii. For large radii, you see that this ratio of bulk viscous pressure divided by rho h, or essentially this could be also understood as the Reynolds number, and or the relativistic Reynolds number in the problem. You see that this relativistic Reynolds number for large radii is essentially converging to a constant value. And this is happening due to the large relaxation times that we are employing in this simulation, namely due to the fact that the relaxation time is increasing very, very sharply. Essentially, tau is not able to, sorry, not tau, but rather pi is not able to have some evolution with radius and is frozen at a constant value. But if you go now to lower radii, of course, also tau becomes lower, and pi essentially is warming up, so to say, and is able to converge to its Navier-Stokes value towards the horizon. And you see that, for example, in the inset plot of the left plot, where if you focus on, for example, the red curves, which is the low viscosity model, you see that the solid line and the dashed line essentially converge, which shows you that pi is converging towards the Navier-Stokes value towards the horizon. Also, we can measure the effect of the relaxation time on this converging procedure, and we show that on the right, where we show, for example, the bulk viscous pressure divided by its Navier-Stokes value and the logarithm of that. And here we see that in the middle we see that essentially only the relaxation time is playing a role when looking at this quantity. So all the models having the same relaxation time, namely ref, low viscosity, and high viscosity, are plotted on top of each other because they have the same relaxation time. In the inset plot, you see that for the reference relaxation time, you get a convergence of around 75%. You get a convergence of around 75% towards the horizon. And with the low, if you compare that with the low relaxation time case, you see that convergence, or the relaxation towards its Navier-Stokes value, is starting much earlier, and also a much higher degree of convergence can be reached of about 90%. And on the opposite of that, of course, if you have a too high relaxation time, the bulk viscous pressure is essentially not able to reach its Navier-Stokes value and is thus stuck below 10%, as you can see in the dark blue plot for the high relaxation time case. A final thing that I want to remark is, if you measure the numeric, since we are using since all of those plots were generated with bug, and we want to measure the numerical error of that, we have seen that the largest errors for pi are of about 30%, which is quite large, and they don't decrease with resolution, which is a current problem that we are working on in this on this whole project. Finally, I want also to motivate why we are actually using this weird prescription for the relaxation time, where the relaxation time is going like r to the power of 3. So if we have a too low relaxation time, I'm showing you what happens in those two plots. So on the left, you see the specific enthalpy as a function of radius. And on the right plot, you again see the Reynolds number, or pi divided by rho h, as a function of radius. So if your relaxation time is not high enough at large radii, essentially pi is not frozen in. And as you can see in the right plot, pi is increasing very sharply and eventually reaching values above 1, where your prescription for non-perfect fluids is essentially not valid. And of course, this will lead to an unphysical behavior, for example, a specific enthalpy in the left plot, which is below 1. And the whole core of this problem is the entropy generation along the flow of the fluid. So as we have constructed our equations for non-perfect fluid dynamics by the assumption that entropy is always increasing in the direction of flow. Right? Since we are looking at the stationary problem here, there is no actually the important time coordinate gets replaced by the radius coordinate, such that entropy is not anymore increasing in the direction of flow, which means for an observer sitting for an observer having the same velocity as the fluid means an increase of entropy over time. Since we don't have the time derivatives anymore, the role of the time derivative is now playing the radial coordinate, which means that entropy is always increasing towards the direction of flow, which means towards lower radii, because the fluid is flowing from outside towards the black hole. According to that, entropy has to decrease for large radii because we are going against the direction of flow. And this is the whole this is at the core of the problem, because pi starts to increase very rapidly for large radii if it is not frozen sufficiently early. I guess I will skip this slide and finally move on to the summary. So to summarize, what we have done is, or what I've presented today, is a conservative 3+1 formulation of the equations of Israel from 1976, which are equations for non-perfect fluid dynamics. And those equations are suitable for the numerical solution combined with the solution of Einstein's equation. Then we have implemented an equation for a simple equation for bulk viscosity of second order type in our GRMHD code and verified the implementation by special relativistic tests. Especially shocks have been, and the Bjerken flow has been simulated. And to further test our equation, we have looked at the viscous black hole accretion problem, which we have first solved with an ordinary differential equation solver, and then have seen that BAC is giving quite good agreement, but there are still some numerical, there are some errors in the errors present, which don't have a converging nature, and this has to be investigated further. Thank you very much for your attention.
Thank you, Mikhail, sorry, for the nice presentation. We have time for questions, and please raise your hands if you have questions, and do not be shy.
And if we don't have any hands, what shall we do?
Yes, this is if you have a question, please go on.
Okay, thank you, Mikael, for the nice presentation. As Masoud said, I'm Neda, and I have a question about this relaxation. I have actually two questions. The first one is about these relaxation times, which you have always in all your slides. For example, you had written tau pi is equal 15 times zeta over 16p in one of the slides.
Yes.
Is it correct? Yeah. What is this p?
This is the pressure.
The pressure. And you said that one can calculate this kind of relaxation time? Just
yes.
And how?
And so this the coefficients for those relaxation time are actually a little bit tuned. So usually I compared my test cases with the relativistic lattice-Boltzmann method, which I found in the literature. Mm-hmm. This data was actually provided for shear viscosity, but since those were one-dimensional tests, it's actually doesn't matter whether you evolve shear or bulk viscosity, because in the one-dimensional test case, those equations are essentially the same. You just have to modify the transport coefficients by a suitable factor, and this is why those odd numbers like 4/3 or 15 divided by 16 occur in this equation. And furthermore, this relaxation time, I think, could be derived by requiring a constant collision cross-section, I think. And then this was the mean free time, between collisions. Yes, I'm not very sure about the details, since I've just picked up the relaxation time in order to perform the numerical simulation. Okay. But I can point to a reference if you wish.
The second question is about this. You speak everywhere about these shocks, and the question is whether this kind of shocks can also happens in the. First of all, what's the origin? Can you little more explain this? And the question is whether this kind of shocks can happen also in the QGP, in the quark-gluon plasma, in the heavy ion collisions and so on.
So,
do you have any idea about it?
The natural, to the first part of the question, those shocks naturally occur in nonlinear equations, because I think because characteristics merge at a certain point. So this is a characteristic feature of nonlinear partial differential equations, and shock waves, I think, can also. I'm not an expert on heavy ion collisions, but I know that shock waves actually have been investigated in heavy ion collisions, and Mach cones also have been investigated.
I see.
I'm not really an expert on this topic, but yes, but I think people have thought about the evolution of shocks and whether those shocks can leave measurable observables in the evolution of the quark-gluon plasma.
I think in your group, the Barbara Betts had done this, the Mach cones. Is it true?
I know Barbara Betts. I remember. I don't maybe I'm not aware of that paper, since I'm also actually more related to astrophysics rather than heavy ion collisions.
No, Barbara, I don't think so. Barbara Betts. Well,
I don't. So I think I don't know her personally, and but I'm not. Yes, I'm not really sure. I would have to look that up.
Okay. So thank you. That's all. Thank you.
Thank you.
So other questions? Mernush, you asked me a question that you can sorry, you can actually ask the speaker.
Okay, thank you, Mr. Chabanov, for your great speech. I didn't understand much about the slide about the difference between pi in Navier-Stokes and pi in your calculations. You did not use your crosser, and I couldn't follow your talk. Could
You mean on this
please
slide?
explain it? No, the diagram slide that in the last of your talk. I don't know what slide exactly.
The results.
Yeah, in the results, I guess.
Ah, you mean here?
No, next one or yeah, this one.
This one?
No, the last one. Excuse me. I think there's a delay, and I saw the last one of in the 28. Okay.
Okay, right. So what I wanted to show here is essentially that that the bulk viscous pressure is converging towards its Navier-Stokes value as soon as the relaxation time becomes low enough. I think this is the only point that I wanted to make in this right plot. If you are I guess you are referring to the right plot.
No, I was referring to the left plot because I didn't understand the difference between that plot that has border inside that bigger plot.
So the inside plot is just a zoomed in region at low radius. So essentially, the big plot is just a zoomed in region of from the event horizon to approximately 6 times the event horizon, and this is really just what is happening or what is going on in this close region here, close to 0 in the big plot, because you can't really see it there.
Thank you so much.
Okay.
So is there other questions? If not, I want to ask some questions myself, actually. And one is that if you have somewhere that the Reynolds number goes to 0,
so in the right plot, this is the logarithm of the Reynolds number.
But it doesn't go to 0.
No, it's the Reynolds number does not go to 0.
Yeah, because this is I was thinking that if that happens, this is a problem for DNMR, for example. So we have some I saw some new paper in the context of heavy ion collisions that is using DNMR for bulk viscosity. But this is interesting that they have this freezing of non-equilibrium physics near the critical temperature. It's very similar to your case that the pi is frozen when it goes to some. Your one is frozen at large radii, but their one is frozen near the critical point, critical temperature actually. And also, but they see something like a divergence of the inverse Reynolds number that is probably against the philosophy of DNMR. But I can see that DNMR may work here well because it probably can resolve the problem of your weak relaxation time. You have it in the next, I guess, next slide.
Yes, you mean by the inclusion of further terms?
Yes, but it's probable. I mean, here actually the Reynolds number in the right hand side is growing, yeah?
Yes.
So if you have an expansion in the inverse Reynolds number, it's a good expansion. But the thing that I can say about the prescription for the relaxation time, it must go to infinity at somewhere. It must diverge if you want to freeze, even in that case. So it's essentially the same thing, and I don't know, but maybe more physical. I don't know.
Yeah, this sounds very interesting, but I'm unfortunately not familiar with the paper.
Yeah, I will send you the paper, but it's actually, as I said before, it's the fault from the particle physicist part, not from the astrophysics or hydro simulations. Another question that I wanted to ask is that can you use this code in the simulation of mergers? How far are you from that?
Sorry?
How far are you from simulating the mergers with bulk viscosity?
Yeah, well, this equation has to be implemented first, and I have been working on BAC so far.
Mm-hmm.
So using BAC, you can't do mergers because you need to evolve space-time. And this is a whole new beast. And usually, yeah, you need a new code for that.
Okay. Thank you. So if there are no other questions, we can stop the recording, and if you have any non-official